All right, let's talk about something really cool today. We're diving into a technology that's the secret sauce behind some of the most reliable systems on the planet. Think massive telecom networks and messaging apps that just never seem to go down. We are talking about Erlang/OTP, and its pretty unique approach to building software that can actually heal itself.
So let's just start with a big question right up front. How in the world do you build a system that doesn't just fall over when something goes wrong, but can actually recover all on its own with no human intervention? I mean, that's a massive challenge in software, right? And it's the exact problem that Erlang and its OTP framework were born to solve.
You see, the whole idea behind OTP is a total mindset shift. It doesn't treat failure like some catastrophe you have to avoid at all costs. Nope, instead, it assumes failure is a normal, everyday event. The entire philosophy is built from the ground up to just expect things to break and to handle it gracefully and automatically when they do. Okay, so to really get how this works, we're going to build the whole concept from the bottom up. We'll start with the most basic piece, the process. Then we'll look at the safety net, which are the supervisors. After that, we'll talk about the blueprints they use, called behaviors, and finally, how we package it all together into something called an application.
First things first, processes. Now, in the world of Erlang, a process isn't what you might think from other programming languages. It is the absolute bedrock of everything else we're going to talk about. And it's what gives us massive concurrency and, this is the important part, isolation.
The key word here is lightweight. Seriously, we're not talking about those heavy, clunky operating system threads. Erlang processes are so incredibly efficient that you can have literally millions of them running on a single machine and it just hums along. They were designed for a world where you have tons of things happening all at once. And this is where it gets really interesting. Just look at this comparison, especially that last column, isolated memory. Unlike traditional threads that often share memory, which means one can easily mess up another, Erlang processes are completely separate. They share absolutely nothing. This isolation, this is the secret sauce for fault tolerance. Because nothing is shared, a crash in one process cannot possibly corrupt the memory of another. It's like having a perfect firewall between every single task. They can only talk to each other by sending messages, kind of like passing notes in class. They can't directly reach in and mess with each other's state. Okay, so if processes are isolated, that's great for containing a problem. But what actually happens when one of them inevitably fails? Well, this is where the real magic of OTP kicks in. This is where we talk about supervisors.
So in OTP, you basically have two kinds of processes. You've got your workers, and they're the ones doing the actual work. Handling a request, crunching some data, whatever. And then you have supervisors. These are special processes that don't do any of that work. Their one and only job is to watch the workers. And if a worker crashes, the supervisor's job is to restart it. Simple as that.
But it doesn't stop there. You don't just have one supervisor watching a bunch of workers. You build what's called a supervision tree. It's this beautiful hierarchy where supervisors can watch workers, but they can also watch other supervisors. This creates these amazing layers of resilience all through your system. This chart shows it perfectly. See, you've got a top supervisor watching a worker and another supervisor, Supervisor A. And Supervisor A is watching its own set of workers and even another supervisor down the line. So if worker 3 down at the bottom fails, Supervisor B just restarts it. If Supervisor B itself fails for some reason, Supervisor A restarts it. The failure gets handled at the lowest possible level, which stops it from bubbling up and taking down the whole system. It's genius. Now, you might be thinking, wow, setting up all these workers and supervisors sounds kind of complicated. Well, it would be, but OTP gives us these standardized templates or blueprints for these very common patterns. And they're called behaviors. The idea behind a behavior is really clever. It basically splits the code in two. OTP provides the generic, battle-tested part, like the abstract logic for how a server works or how a supervisor should restart its children. Then, all you have to do is write the specific part, your actual business logic, in what's called a callback module. And this slide shows you the payoff. On the left, without behaviors, you've got everything tangled up in one big file. It's a mess. But on the right, the generic server logic is handled by OTP, and you just focus on writing the little bit of code that's unique to your problem. It's so much cleaner, safer, and way more reusable. And OTP comes with a whole set of these right out of the box. Gen server is that client-server pattern we just saw. There's stuff for state machines, for event handling, and of course, the supervisor behavior is what you use to actually build the nodes in that supervision tree. You're building with proven, reliable parts from the start.
Okay, let's zoom out one last time. We've got our isolated processes, they're being watched by supervision trees, and we're building them with standard behaviors. So how do we package all of this into a single deployable thing? Well, that's where applications come into play.
In OTP, an application is basically the whole package. It's a component that bundles up a supervision tree and all the code that goes with it. You can think of it like a self-contained service. It's a single unit that you can start, stop, and even reuse in other systems. It's really the highest level of organization.
So let's just take a second and put all these pieces together. Let's look at the full picture of how OTP lets us build these incredibly resilient systems, not by accident, but by design.
It's really such an elegant, layered approach. You start with isolated processes, so one failure can't cause a domino effect. You add supervisors on top to automatically clean up any messes. You use standard behaviors so you're not constantly reinventing the wheel and introducing new bugs. And finally, you package it all up into a neat, reusable application. Each layer builds on the one before it to create this fault-tolerant whole.
And that really brings us to the most important takeaway. In so many other systems, we build the thing first, and then we try to figure out how to make it reliable later. We try to bolt on fault tolerance at the end. In Erlang/OTP, it's not an add-on, it's not an afterthought. It is the bedrock. It's the foundation that everything else is built on.
So I guess I'll just leave you with this thought. We spend so much of our time trying to prevent every single possible error from ever happening. But what if we didn't? What if we just accepted that things will fail and instead designed our systems to embrace that failure, to manage it, and to heal from it, all on their own? That's the powerful idea that Erlang/OTP brings to the table.